Hello, good morning, good afternoon, good evening, everyone, wherever you might be. It is my great pleasure to welcome ELMAR SCHROHE from Hannover, Leibniz Universität, and he will speak about his joint work with Richard Ness. I think that every second talk is based on joint work with Richard Ness.
Yeah. No, it's not true. It's not true, period.
Okay. But anyway, he will preserve order. There must be order. So order preserving automorphisms of Shubin type pseudodifferential operators. ELMAR, the floor is yours. Take it away.
Thanks a lot. Thanks a lot for the invitation. It's a great pleasure to speak there. As you said already, joint work with not only Richard Ness, but also a PhD student from here, Robert Hesse.
And he's right here. He's present.
He's right here. Okay.
Yes.
So what I want to talk about is a theorem that actually goes back to Dijsselmaat and Singer. It's from 1976. Was published in Communication Pure and Applied Mathematics, and it says the following. So you have two Z-infinity manifolds. They need not be compact, called X and Y, and you have a cohomological condition on X, namely the first cohomology class of the cotangent cosphere bundle vanishes. And they say every order-preserving isomorphism from L infinity X, I'll explain what they mean, to L infinity Y is of a special form, namely it's given by conjugation with an invertible, elliptic, properly supported Fourier integral operator A, which is a map from C infinity Y to C infinity X. And they have a little footnote here, and they say see Hermander for the definition of Fourier integral operators. So at that time, he was not so famous that you would not misspell his name. And actually, this topic was taken up more recently by Matthias and Melrose in an article in Duke Mathematical Journal, where they showed a bit more than this, but also came back to this old theorem and gave a new proof for the case that X and Y are compact manifolds, but more generally that the operators are not only scalar, but vector bundle valued. It turns out vector bundle value doesn't make a big difference, so I stay here with scalar symbols. Okay, the usual pictures, you have Dijsselmaat on the left, Singer in the middle, and Hermander. Okay, you probably have seen these pictures before. So I want to say a little bit about this theorem and actually present the proof and then show what's new for the Shubin case. So we go to Dijsselmaat and Singer's result. And okay, to explain what they're doing, of course, you all know what pseudodifferential operators are, but since this is a special class that's not so much in use these days, let me go back to the definition. What they consider are symbols P, and the symbol in this sense is a smooth function on Rn times Rn. Once we are on Rn, that might have a complex order M, and satisfies the standard estimate. So if you take derivatives with respect to xi and derivatives with respect to x of this function p, then you can estimate them by 1 plus xi absolute value to the power, well, if m is complex, you take the real part of m. Oh, sorry, this is wrong. There shouldn't be a minus beta here. I'm sorry. Can you raise it, Piotr?
Give me a second, yes. Annotate. So you don't want this minus?
I don't want this minus beta. No, this is wrong. This is a copy paste error.
Okay.
Okay. All right. Perfect. So, and here you estimate them locally. So for each compact set, you estimate this for X in the compact set and then xi in Rn. Okay, and of course they only work with classical symbols, so the symbols have an expansion into homogeneous terms. So P is an asymptotic sum of terms Pm minus J, where each of these terms in the expansion is positively homogeneous of a certain degree k in psi for psi non-zero. So this means if you multiply psi by a positive constant, then you can take it out with the power k. Okay, for these we write p in Sm. That's the usual thing. And the top term in this expansion, so this is Pm, that's called the principal symbol. And in all this text, they only consider classical symbols. Okay, there's a notion, of course, of operators. And the thing is, if you have a symbol in Sm, you obtain an operator, Rp. Okay, you just take a compactly supported function Rn, map it to a smooth function Rn by this standard formula. So you take the Fourier transform of your function u in psi, multiply by the symbol, that should be a p actually, by e to the ax psi, and you fix the constant for the Fourier transform, so that it works out. So this is the standard. Thanks, Berse. So this is the standard formula, and the point is, so you map this from CC infinity Rn to CRn. So you actually only have a map from, if you extend it from E prime to D prime. And whatever way you do it, in general, you cannot compose these operators. So one goes back to a notion of proper support, and you call such an operator properly supported if it maps not E prime to D prime, but E prime to E prime. Or if you go over to dual spaces, C infinity to C infinity. So proper support you can also describe if you look at the Schwarz kernel of the operator. Take a point xy in the support of the Schwarz kernel, map it to the first component x, and look at this map. And if this map is a proper map, then you call it properly supported. So this is how this terms comes about. What you actually need is that you have this mapping property. And once you have this mapping property, you can compose the operators. So that's the point of this proper support. Proper support is not a big deal. In particular, if you deal with pseudo-differential operators, then most of the time you just work with a symbol. And you can always achieve proper support by changing the operator by an operator with a smooth integral kernel. Well, that you don't see in the symbol expansion. So most of the time you just don't care about it. Okay, so far for proper support. Of course, this concept can be taken to manifolds, and that's what they do. Since you have these non-uniformly estimated symbols, you can just use any changes of coordinates and it works fine. So you use a partition of unity, you localize, and then you get the operators on manifolds. Okay. Then the notation, they use the Sherman notation for the operator classes. You have operators of order m denoted by Lm of x for your manifold x. Where now if we look at the operators that turn up in the theorem, then we just take m integers. Okay, we want them properly supported, and then we have operators from E prime of x to E prime of x, and they are induced by the local symbols. So you call it of order m if it has a symbol of order m. And L infinity is just the union of all of those. Okay, I guess that's clear. And so what they mean by order preserving, well, that's also fairly clear. We have the order here. And if you have two manifolds x and y and such a map from the operators on x to the operators of y, then you call them order preserving if actually the image of the operators of order m on x are just the operators of order m on y. So this is a nice notation. So let's have a look again at the At the theorem, we understand the notation here, order preserving.
Can I ask a simple question?
Sure.
So you have to target the image, the range should be the whole L M of
Yeah,
Y,
right.
or it's included in L?
No, their condition is that it's a full thing.
Okay.
Okay, we understand this notation. So these are just all pseudo-differential operators. We saw what properly supported means, even though we have not yet talked about Fourier integral operators. And so, yeah, the surprising thing is that actually this isomorphism is given by conjugation by an operator. Okay, and that's maybe the first surprising thing, and that's an algebraic fact, which is they refer to as Adelheit's lemma, and I've stated it here because we needed two contexts. You can use it in many contexts actually. You have a Frechet space E. Dimension has to be greater than 2. Well, usually you have function spaces, so that's not an obstacle. And you have a subalgebra of L of E, for which, okay, there comes the only sort of non-trivial condition here. You look at these rank 1 tensors. So you look at these tensors U tensor V, where V is an element in E prime and U is an element in E. So these naturally form a subset of this algebra, and you consider all those V such that U tensor V is in A for all U. And you assume, this is the assumption, that this is a dense subset of E prime, the dual space. Okay, that's the situation. And then you have two other of the same kind. So you have another Frechet space E tilde and another algebra A tilde with the same properties. And then the statement says, whenever you have an algebra isomorphism, so just algebraic, right? I from A to L tilde, then it's necessarily given by conjugation with an element. And this A, of course, it's invertible, but it's automatically continuous from E tilde to E, and it's even unique up to a constant. Of course, constant has to be non-zero. So we can apply this here. When we choose this Frechet space E to be C infinity X, the algebra is just all pseudo-differential operators. We could also take, for example, L minus infinity. That would also work. So you have some choice of doing this, and taking for F. Okay, or F then is the complexly supported C infinity functions. Then you could do the same thing, of course, for Y. And you see from Adelheit's statement that IFP is given by an operator A inverse PA for some continuous invertible A that maps C infinity Y to C infinity X. Okay, because it maps C infinity Y to C infinity X, it's automatically properly supported. That you can characterize the proper support just by this statement, right? It's the same as saying E prime to E prime for the adjoint. So, and continuity comes for free. Quite a nice fact.
Sorry, I have a quick question. This F is no longer Frechet, yes? C infinity with compact support is no longer Frechet, or correct me?
No.
Okay.
No. This is an inductive topology, right? It's
not countable.
Yes. Yeah, uncountable. Yeah. No, but only E has to be Frechet, right?
Mm-hmm. I see. Mm-hmm. Thank you.
Okay, so we understand a bit more of this theorem. It's given by conjugation. We know that's clear from Eidelheit for such an operator that we see. So it remains to show that's actually a free integral operator. We also know if it's some operator, then it's properly supported. That came for free, right? That's what we know already. Okay, so the question is, why is this a free integral operator? And the somewhat surprising fact is that comes merely from the fact that the order is preserved. And that's such a nice argument that I want to show it. And so let's look. It's 3 steps, and they will actually take a little while to say, but let me give an outline of the 3 steps. The first is, okay, whatever m you take, you can look at the quotient of Lm mod Lm minus 1. And then since you know that these spaces are mapped to each other, you get a map from Lmx mod Lmy, mod Lm minus 1x to Lmy mod Lm minus 1y. And from this, we're going to conclude that I induces a canonical transformation on the cotangent space with the 0 section removed. Okay, it's going to take a few steps, but that's the background. The next step is, once we have such a canonical transformation, we can associate the free integral operator, which gives us a first approximation to this A. And then comes a bit of work that we're not going to do in detail very much, but you can then refine this A by an iteration procedure, this first approximation by an iteration procedure to get the A. So that's the strategy. But the first step and the most interesting one is to really get this canonical transformation. So how do we get this? We get it in 2 steps, actually. The first is we look at the 0 order operators modulo the -1 order operators. And then, of course, we know if we take the quotient, well, that's basically the 0 homogeneous function on the cotangent bundle, which you can easily identify with the smooth function on the cosphere bundle. So the principal symbol map gives us an isomorphism from L0 mod L minus 1 to C infinity of the cotangent of the cosphere bundle. Okay, the cosphere bundle here just is the quotient of the cotangent bundle mod the R plus action. Okay, so actually our isomorphism I on the pseudo-differential operators gives us an algebra isomorphism from Z infinity of the cospheres to Z infinity of the other cosphere. Well, if it's an algebra isomorphism, then it has to preserve maximal ideals. But the maximal ideals here we know very well. They're just given by functions vanishing at a point. So what we get is we get a map actually from the points of S star X to the points of S star Y. But since it maps smooth function to smooth function, these are symbols, we see that's not just a map, but it's smooth. And of course, it's invertible in both directions. So it's a diffeomorphism. So by this very simple argument, you get already a diffeomorphism from S star X to S star Y. And the point is, of course, this says precisely that if I take the principal symbol of the image of a 0 order operator, then it's the principal symbol of the operator composed with, well, just the inverse of C, right? Because C goes from S star X to S star Y. So this is an operator on Y, and the symbol then is a function in C infinity S star Y, and you get it by composing the symbol of P with this map C inverse. So that's the first step, very easy. So how do you get from this to canonical transformation? Well, I inserted the slide. What is the canonical transformation? In case somebody is not so familiar with that. Okay, just to say a little bit. Okay, if we take the cotangent space, remove the zero section, then we have a symplectic manifold, and the symplectic form is the standard form. We call it omega. So d psi j, which dxj. That probably you know from your basic courses. You can do the same thing on y, and a canonical transformation then just is a map C from T star X to T star Y, both times zero section removed. That is not only a diffeomorphism, but also preserves the symplectic form. So it's a symplectomorphism, and moreover, it's one homogeneous in the fibers. And one homogeneity in the fibers here just means that if X psi goes to Y eta, then X lambda psi goes to Y lambda eta for any positive lambda. So it's positively one homogeneous in the fibers. Okay, so our question is, we have this map from S star X to S star Y. How do we get this to a map from T star X to T star Y? So basically we need the scaling in the fibers. And this scaling in the fibers, well, we get it with the help of order reducing operators. Okay, so what you need to know about the calculus is that there are invertible operators of order 1, such that the inverse is of order -1. Okay, such operators you can find, for example, take 1 minus the Laplacian and the square root of that. Okay, you know, okay, so choose on your manifold a metric that makes it complete, and then take the Laplacian, then it's self-adjoint. You take the square root of 1 minus Laplacian, and that's a good operator. It's of order 1, and you show the inverse for the -1. Okay, if the operator is invertible, and you look at the image, then, well, necessarily the image is also invertible. So, and what, of course, we also know, the operators of order 1 are simply given by multiplying any element of order 0 with this one particular element of order 1. So this element just shifts any, gives us any order operator by just using a power of this operator alone. Okay, and we proceed now in the same way as before, but now we consider not L0 mod L -1, but rather L1 mod L0. And here the situation is slightly trickier because L1 mod L0 by the principal symbol is isomorphic to the one homogeneous functions on the cotangent bundle. Of course, if you get one homogeneity, you could also identify it with smooth functions on the closed sphere, but in that case, that wouldn't help. So this is the smarter point of looking at it. So take one homogeneous function on T star X. Well, you all know if you take the symbol of the commutator, then you get the Poisson bracket at least up to a factor of -i. Okay, here, so if I take the commutator of two operators P and Q, with them builds little p and little q, then this is the formula. Okay, if we go to this fact here that L1 is just given by lifting L0 by a function by this operator lambda x, we see if we take the symbols of this, then this map I bar, you know, this map that we have here, sends lambda x times p. So this is the symbol of this operator here. so lambda x times p, to lambda y times, now p is of order 0, and we know already what happens with zero order operators, namely their symbol is just given by composition of, composition of p with C inverse. So we get this simple formula. Now, a little trickier, you can do the whole thing for commutators. The next formula is this trickier version. What you actually do is, okay, here take the symbol of a commutator of these elements multiplied by lambda x inverse. Okay, this thing is of order 0. So its symbol is given, okay, if we compose it, that's the symbol of I of the corresponding operator here. So lambda x times this. So this whole thing is, this is lambda y. This is of this form here, something composed with lambda inverse. So this is the same as this one, as this commutator here. Okay, at first it takes a while to digest that, but let's just take the formula for granted. There's nothing serious about it, but it's very nice and tricky to do it this way. The whole paper is nice and tricky. So let's look at this formula. I have it again on the next slide. So this is the formula copied from before. Okay, now the point is we want to lift our map C to the cotangent bundle, and we have to do the scaling. In order to get the scaling, for the scaling, you can only use positive scalars. So we want this lambda x to be real. That's not a problem. As I said, you can take 1 minus delta to the power 1/2, then you have a positive symbol. That's fine, and real, everything is good. Okay, we have this formula here. That's the formula we copied from above. And now you can simply take p equal to 1. Okay, formula is still valid. So this thing here vanishes because it's just 1. And here, I guess, here I have the Poisson bracket of this. If you compute this, you get this formula here. So again, you have to compute a little bit. But the point is if lambda x is real and q is real, then the Poisson bracket is real. This whole right-hand side is real. So we see that this here is real for any real q. So of course, this gives you differential equations for lambda y, but we see that all the derivatives of the imaginary part are 0, so the imaginary part is constant, and so it has to be 0 because it's one homogeneous, and so lambda y is real. So it's a nice tricky argument to simply look at this thing here. Okay, so lambda y is real. Now this far we followed the argument of Dijkstraat and Singer. Now you want to conclude that lambda y is actually also positive if you start with a positive lambda x. And they didn't see this, and Mattei and Melrose gave a very nice argument. Okay, first thing, maybe I should go back a little bit. We assume that n is larger than 1. Then the crosphere is connected. Sure.
May I ask why? It's completely independent of connectivity of X?
Say it again.
May I ask why it is connected? Is it completely independent of the connectivity or non-connectivity of X?
Okay. That's actually true. No, we assume. I guess we should assume X to be connected.
Okay.
Yeah. Sorry.
Sanity check. Yeah.
And then you conclude, okay, if it's connected, then it's either everywhere positive or everywhere negative, right? Because it has to be elliptic, and so it cannot vanish at one point. So we know it's real. It's either positive or negative. And then Mattei and Melrose came up with a very nice argument. So if lambda y were actually everywhere negative, then lambda y, which is an unbounded operator, right? Because it's first order, would have a spectrum with very large negative real part. But on the other hand, it has to agree with the spectrum of lambda x, because lambda y is the image of lambda x, so they have the same spectrum. But the spectrum of lambda x is essentially positive, so we conclude that the symbol has to be everywhere positive. Oh, sorry. Lambda, this should be a y. This should be a y. Is everywhere positive. Okay. So the fact.
So here you mean lambda y, right? Here.
Here, yeah.
Okay.
That's very good. Well, no.
Yeah. Well, when you move it, I have to.
What this does is you can simply extend. You can use this now. That lambda y is positive, lambda x is positive. So you can simply extend C to the cotangent bundle by asking that lambda y is lambda x composed with C inverse. So the same formula that we had, this is the formula we had for the zero order symbols. You just take this here, and then if you plug it into the thing we had before, you see that we have the bracket of P composed with C inverse, Q composed with C inverse, is the bracket of PQ composed with C inverse. So that's the formula we had from above, right? Where's the formula? This is this formula here now applied with this. Okay, if we look at this, we see right away, well, what does it say? It says that the Poisson bracket is preserved. So this works for all first order symbols. So this C here, or rather the C inverse, is a canonical transformation. But if C inverse is a canonical transformation, then also C is a canonical transformation. And we see right away that we have the formula we had before, but now for all operators, well, at first we get them for first order operators, but then we can iterate this and we get them for all orders. So that's nice. So we know the symbol of the image is always the symbol of the operator composed with this canonical transformation. And that was our first main step. Okay, what do we do with this canonical transformation? We have to get a Fourier integral operator. I don't want to say too much of Fourier integral operators, but first I want to say what we actually need. So if you're not familiar with Fourier integral operators, then you can just take this as standard facts, and that's good enough. The point is, if you have a canonical transformation, you find an elliptic Fourier integral operator, FC, associated to this canonical transformation. You'll see in a second what I mean by associated to that, which is a map from C infinity X to C infinity Y, and a corresponding operator with the inverse canonical transformation. So it goes in the reverse direction from C infinity Y to C infinity X. That are almost inverse to each other. So FC inverse is identity mod something regularizing, and the same for the reverse order FC inverse. FC is also identity modular regularizing. So, and the point is, okay, if they associate with this canonical transformation, then Yegov's theorem says, whenever you have a pseudo-differential operator, now in this case on Y, and you conjugate it by this, okay, they need not really be inverses of each other. It's sufficient if they have this property here. Then the conjugation gives you again an operator of the same order, and you can also determine the principal symbol. That's Yegov's theorem. The principal symbol of this is just the principal symbol of Q composed with the canonical transformation C. Okay, I've said it this way here because we now want to apply this to our fact. So here we see that basically our isomorphism composed the symbol with C inverse, and we see that by conjugating it with the Fourier integral operator, we can undo this because this conjugates it by C. So that allows it actually to reduce the whole argument to the case where the manifolds are the same. What do we do? Okay, we have this I, so that's the one that basically composes with C inverse, and we do this conjugation with the FCs that undoes it. So if we take this, the symbol is the same as before. So if I take J of P, this composition here, then the symbol is, the principal symbol is the same. So J of P minus P is of order M minus 1 if P is of order M. And moreover, this is again, J of P is again automorphism. You have to be a little bit careful because you don't have the identity. You could actually achieve that if you wanted. You could perturb this FC or change the FC so that you get something invertible, but that's not necessary. You say, well, it's just taking automorphism of L infinity X mod L minus infinity of X. Okay. Just a bit on Fourier integral operators. So you have a canonical transformation. That's just a map from the cotangent bundle to the cotangent bundle. You look at the graph of this. The graph is the set. Okay, it's the twisted graph. So you take a pair x psi y eta such that C of x psi is y eta, and you flip one of the covariables. Then this is a Lagrangian subspace of the product space. Okay, the point of this flipping is it would, if you have two symplectic forms on T star y and on T star x. And if you would not flip it, it would be Lagrangian with respect to symplectic form of on y minus the symplectic form on x. If you flip it, it's Lagrangian subspace with respect to the form on y plus the form on x. And that's, of course, better because it's the same form than in more coordinates. So, but it's a nuisance to have it, I agree, but it's always the case. Okay, this Lagrangian subspace, you can describe by a phase function. And you can choose, for example, a very nice phase function with a generating function that you might remember from a physics course, minus the standard inner product of x and psi. And then if you have such a phase function, then your Lagrangian just is given by these pairs y dys d psi s and minus psi. So in this sense, you go from canonical transformations to Lagrangians to phase functions. And a Fourier integral operator just is something like a pseudo-differential operator, except that you replace the phase function for a pseudo-differential operator by this more complicated phase function here. Okay, it's a bit annoying here because I have an operator depending on y, because I'm on y. So I have the variables x and y that you know from the standard calculus interchanged. So I integrate over x and psi, and y is the free variable. Okay, I hope you don't mind, but then it fits with the stuff I did before. Questions?
Okay, I have a question.
Yeah, sure.
So this term S of y psi, does it somehow influence the order of this operator, or this
No,
depends on P?
in this case, in the standard case, this is just a one homogeneous function and it's independent of the order. The order of the operator is merely given by this P.
Okay. Okay, thank you.
And how can I see this canonical transformation C on the right-hand side? I mean, it says that it's a Fourier integral operator associated with C.
Yeah.
And so how is C influencing this formula on the right-hand side?
Because you know, this is the graph of C. This L here, the Lagrangian space is the graph of C.
Okay, and that's what you sort of integrate over, right?
So yeah, you have the no. The funny thing is, okay, you have a canonical transformation. The graph of the canonical transformation is a Lagrangian subspace.
Yes.
The Lagrangian subspace you describe by a phase function, namely this one here.
Okay, so this is in S. Okay.
And this phase function insert here, and that in that sense it's associated with it.
Yeah, there's too many steps and I got lost. Yes, okay.
No. We're not in big hurry, right?
Yeah, no, not at all. We have still 47 minutes or something.
Okay, maybe I should. Okay. So this is how this Fourier integral operator business works. Okay, now comes the hairy part, and I'm going to skip that. But what would we know is, okay, that's what I had on the slide before. If we conjugate I of P with this Fourier integral operator, then we get a map, just L infinity x to L infinity x. So we got rid of y. That preserves the principal symbol. You know, if P was in Lm, J of P minus P is in Lm minus 1. And we get an automorphism of this. And now comes the fact you want to improve this. You want to improve it so that J of P is P up to order minus infinity. And that's a rather tricky iteration scheme that also Mattei and Melrose did not touch at all. The point is, this is the only time a Fourier integral operator comes in. So, and you see, you have quite some freedom in choosing this Fourier integral operator. You just need your canonical transformation. You pick any Fourier integral operator associated with this canonical transformation, conjugate with it, and that does the job. All we do now is change this by a pseudo-differential operator. And we know the composition of a pseudo-differential operator and the Fourier integral operator is again a Fourier integral operator, and they are actually associated with the same phase. So, and the same Lagrangian submanifold. Okay, the point is, okay, you iterate this thing to make this better. So you find an elliptic pseudo-differential operator and the parametrics or approximate inverse in the sense that, you know, Q and Q sharp are inverses of each other modulo smoothing operators. And then if you conjugate again, So this was our first conjugation. If you conjugate again with this Q sharp and Q, then we have this identity up to L minus infinity. So they do this actually step by step. You improve every step by order 1, and then by asymptotic summation, you get this up to order minus infinity. Okay, that's a tricky thing to do, but very nice.
Sorry, I have
a
very simple question. So, what happens if this canonical transformation is the identity? We get that S is 0. When we get that the Fourier integral operator is...
let me just go back. That was here. If then S y psi is just y psi. So that's this. If it's the identity, then you get just this phase here. Okay, you see it also. You know, if it's the identity, then okay, let's see what happens. You have y here. Then if we take y this, then dy dy s is just psi. So if y here, psi here, d psi s is y. Is d psi s is y minus x, and so you get y minus x here and minus psi, but I forgot there should be this should be on the set where the psi derivative is 0. I'm sorry, and that means that
x equals y.
X equals y, yeah. Okay.
And
so
also this case corresponds to the fact that C is identity or not, because somehow this S is hidden in this L, yes? So you start with C, a canonical transformation, then with respect to this canonical transformation, you get the Lagrangian subspace, and then after having this Lagrangian subspace, then you arrive at this S. So somehow this S is implicit and comes from this C. So the simplest case is when C is identity, yes, then this S is also identity, yes?
This S should be
product, sorry, not identities. Just,
this should be the phase when S is the identity. When C is the identity.
Okay.
Let's see. Here get psi. That's correct. So y psi, and you should get y minus psi. But somehow there's a problem here in that I get y minus x. I somehow made them.
But the S is only the first part of your phase function down there. So the S is just the y psi. So you're good. Like
so
what we wrote down in the last line is the phi.
Yeah, thanks. So thanks. Yeah.
Hey.
Sorry.
Okay,
yeah, because this was the addition. Yeah. Okay. Now it fits, right? So we get y psi, y minus psi, and the minus comes from the fact that we switch the graph. So it's the identity. It's okay.
Go ahead.
Okay, thank you.
Sure.
We have a question. Tomek, go ahead.
Sorry, it's not a question, it's a maybe comment. Could you come back to the previous page?
Yeah.
Yeah, instead of inverting this psi, you could take a symplectic structure, which is the difference of the symplectic structures, and then it would this L being identity, the graph of identity would be this Lagrangian submanifold, and then the explanation would be easier. There would be not this problem with this minus.
Yes, but okay, yeah, I said this, right? If you want, you usually want the symplectic form to be the sum of the two, so that it looks the same as the symplectic form on the product space. It's just a little nuisance. There's nothing deep behind it.
Yeah, but there is a convention when the symplectic structure is a difference, and then calculation is easier.
Yeah, I agree, but most people do it
It's
this
all my
way.
comment. Thank you.
Okay, I think I was here. You have these things, you conjugate again, you get order minus infinity. And in this construction, they use this condition that the first cohomology class of the cosphere bundle is 0. Because basically they do local constructions, then they want to patch them, they need this condition. Mattei and Melrose showed that this is not needed if X is compact. So that was a bit of an advantage. So condition is not actually needed. Okay, if we have non-compact manifolds, their argument doesn't work. So in the case that X is non-compact, you must be careful. Okay. Just to see how you conclude, because later we are going to see we do very similar things. Now we have this formula here that was on the slide before. On the other hand, we have Eitelheit, who says that I of P is given by conjugating with some invertible operator. And you see, it's not completely trivial. It's not, okay. But what you see is a nice argument. You take this operator here, and you know that this has an A inverse, right? From Eitelheit's lemma. So you look at Q sharp, FC inverse, A inverse, and you see this multiplied by P. Okay, if you multiply from the right with the parametrics again, minus PE is an L minus infinity. So this is this identity here multiplied with this operator again from the right-hand side. Okay, that you have something like this. So you have an operator that commutes with all pseudodifferential operator up to smoothing elements. Then Dijsselmelter and Singer showed in the standard case, this must be a multiple of the identity for some constant C, and Z is non-zero, and the regularizing operator. That's a little argument, not completely simple, but what you see from it, so this operator here, that has this property, right, is a constant multiple of the identity plus a regularizing operator. You multiply it by A from the right-hand side. You see that CA plus RA, there is an equality sign missing here. Could you help me out again?
Where?
Here, where the cursor is. Sorry.
Okay, yes. So here is equals.
Yeah, thanks.
Okay.
And then you see, you can put this to the other side. So you get this Q sharp FC inverse minus RA to the other side, multiply by C inverse, and you have A. And the funny thing is, you know that this on the right-hand side is a Fourier integral operator. This, you know, is an invertible operator. So the right-hand side is an invertible Fourier integral operator. This is properly supported. So this is properly supported, and everything is done. So you you get part of the properties from Adelheid's lemma and part of it from the theory of vertical operators. Okay, so that's, and any questions so far?
I don't see any raised hands. Good.
Okay, so we come to the Shubin type pseudo-differential operators. And the motivation, there's a motivation for this, because when I worked with Anton Savin, which I still do, we study index theory of operators where you have pseudo-differential operators. In that case, say Shubin pseudo-differential operators with the group action on them. And of course, you want this G to act by automorphisms. And if you want to do index theory for operators of this type, and you don't want to go, everything to go berserk, you want it's a good idea to assume that the order is preserved. So we studied special cases where the group is given by Heisenberg-Weil operators. So this is a representation of Cn, and metaplectic operators, actually complex metaplectic operators given by Un. So the group is the cross product of these two. But you ask, what else can you take in the best possible case? And that raises the question to find the automorphism of this psi. Okay, so that's the motivation behind it. We look at Shubin type symbols, and now the formula is correct that you corrected before. So a simple situation, you work on Rn times Rn, which actually allows you to sometimes really compute something. You take symbols, and the simple estimates differ from those before in that every time you take a derivative, the order goes down by one step. So you take a psi derivative, it goes down. You take an x derivative, it goes also down. As before, we call P classical if we have an asymptotic expansion. The difference in that before is these terms in the asymptotic expansion are positively homogeneous of this degree, m minus j, but now they are homogeneous in both variables, in x and psi, as long as x and psi is non-zero. Okay. You write for the symbol space gamma of m. That's at least what many people do. We do it here. M might be complex. If m is complex, then we would take the real part here. It's actually in the iterative procedure I described before, when we went to these operators Q sharp. These Q sharp are in general of complex order. That's why you need complex orders, even though the algebra itself is only real integer order operators. Okay, PM is the principal symbol. I said this before. The intersection of all those is very nice. The intersection of all these symbols is just the rapidly decreasing functions on Rn. So you have a very nice residual class. Okay, as before, the same formula holds. You don't have to worry about proper support. You get right away operators acting on S of Rn by the standard formula for a pseudo-differential operator. And I just wanted to fix here the notation. By psi m, we denote the operators with symbols of order m. And here for the algebra, we only admit that m is an integer. And of course, as you always do, you take psi infinity is the union of all those, and psi minus infinity is the intersection. Okay, I guess that far is clear. The only thing that's different so far is the symbols are homogeneous in both variables, and you have these very particular estimate that every derivative, whether it's with respect to x or with respect to psi, lowers the order by one. The prototype of these is the harmonic oscillator. So if you have x squared minus delta, that has the symbol x squared plus psi squared. So that's a second order operator in this calculus. One interesting thing, you all know the composition formula for pseudo-differential operators. You know, if you have a symbol of order m and a symbol of order m tilde, you take the composition of the operators, then it's again a pseudo-differential operator, also of Shubin type, of the sum of the orders, and you have this asymptotic expansion formula that everybody has seen before. But what's the difference? Usually, this term goes down in order, and this one does not. But in this case, they both go down in order. So what you see is the principal symbols multiply, but if you look at the next term, as soon as the alpha is non-zero, this goes down one order, and this goes also down one order. So the next terms, and particularly the commutators, are 2 orders lower. Okay. So let's state the result. The result is if you have an automorphism of the algebra of all Shubin type pseudo-differential operators, which is order preserving, so operators of order m go to operators of order m with equality here, then they're given by conjugation again with invertible Fourier integral operators, but it's now an invertible Fourier integral operator of Shubin type, a class that I will introduce below, and that's the formula. So the formula looks exactly as before, and we can actually do much of these things as before, with a few caveats. The first thing is, of course, this is a subclass of the pseudo-differential operators that they considered, right? But of course, they're not invariant under this conjugation, right? If you take conjugation with the standard Fourier integral operator, you get again a pseudo-differential operator, but you leave the Shubin class. You know, if you have these estimates, let's just go back to the estimates. You see right away, even if you want to do coordinate changes, you have to be very careful not to perturb these estimates here. So in that case, this is a very special class. Okay, this class of Fourier integral operators in more special situations has been studied by Helfer in his book on what's it called, Théorie spectrale des opérateurs globalement elliptiques, something like this, and in very special cases also by Cappiello, Scholz, and Barbeck. Okay, how do you proceed? Well, we know Eidelheit's lemma, and Eidelheit's lemma says right away, this isomorphism is given by conjugation with a continuous map. Well, before A was a map from C infinity to C infinity, now it's simply a map from S of Rn to S of Rn. So that we get completely for free. And the task is, of course, as before, we have to see how this A looks like. And we actually follow the approach that I outlined before and look for canonical transformation. The difference is, okay, your symplectic manifold is not, before it was T star X with the zero section removed. Now we take T star N and only remove the point 0 and not the whole section. You see in a second why this is the case. But of course, the symplectic form is the same. Okay, we look at, okay, you see right away where something happens. Same argument as before. I preserves orders. I can look at the quotient of 0 order operators modulo operators of order -1. And they go, oh, sorry, there shouldn't be X and Y. I'm sorry. That was stupid. So because we are always on Rn, So, okay, that's maybe too much to strike out, but okay. So it's always just psi 0 mod psi minus 1 and on Rn. But again, now we look at the principal symbols. The principal symbols are zero homogeneous in X and psi. So now we don't get a map on the cosphere bundle, we get a map on the sphere. So the sphere in Rn times Rn is S2n minus 1. So the map from here to here. And as before, of course, maximal ideals are preserved. So it gives us a map from points to points, and therefore a diffeomorphism from S2n minus 1 to S2n minus 1. And so that for symbols of order 0, the symbol of the image is the symbol composed with this map C inverse. So you see, the argument is roughly the same as before. The outcome is slightly different in that we are on the sphere and not on this cosphere. Now, how did we get from the cosphere to the cotangent bundle? Well, we looked at first order operators. And that's easy, we can do the same thing. The argument changes just in minor points. We have an operator of order 1. Okay, for example, take this harmonic oscillator, add 1 to make it strictly, to make the symbol everywhere strictly positive, and the square root of this, then you have a nice first order invertible operator that does the job. The inverse is of order -1, that's also clear. Okay, the image of it is also invertible and also has real principal symbol. Okay, this Mattei-Melrose argument with the spectrum can be adapted to this case very easily. Okay, for the commutators, we no longer have a Lie algebra, but since the order drops by 2, if I take the commutator of 2 first order operators, then I get a 0 order operators, but it's not affecting the argument because as before, the symbol of the commutator is the Lie bracket of the symbols. So in this case, both of them drop by order 1. And so we have here a 0 homogeneous thing and here 2. So I can actually adapt the same thing and extend C to the to T star n with 0 removed by this formula as before. You know, same thing as before, just the difference is it's 1 homogeneous, but now it's 1 homogeneous in all variables and not just in psi. It preserves the Poisson bracket that comes out of the construction. And we have this formula here for the symbol. The symbol of the image is the symbol composed with the inverse of the canonical transformation, which holds for everything. So same argument as before, just with a different outcome. Okay. So now we have to do four-integral operators, and here things become different. Namely, okay, our canonical transformation is homogeneous of degree 1 in both variables. That was our construction. If we take the twisted graph, or if you prefer to work with the difference of the symplectic forms of the graph, then you have a Lagrangian subspace. And again, this is homogeneous in all variables. So you can scale it in the variables. And the result that you have to prove is, if you take a point in lambda, and actually I should have put the minus sign here, then we can describe this locally by a phase function. So in the sense that the graph lambda is of this type here, where well, we are on the critical set of the phase function. So that's more in the sense of the classical theory of Ramanda. But phi now is not a one homogeneous function as in the standard case, but it's two homogeneous in all variables. How do you get that? Because your Lagrangian is homogeneous in both variables. You choose another one form. You know, usually you have this canonical one form, summation psi j dx j. But that just covers homogeneity in the psi variable. If you want to work with this, you should use this homogeneous, this one form, which satisfies again d alpha is omega, right? Because if you take this here, then you get 1/2 omega. If you take this here, you get the other half omega. And together it works out, right? Because here you get dxj wedge d psi j, which you can move around with the minus sign, and then you get omega. So once you have this, you have the one form, you're on a simply connected space. Because n is larger than 2, you find a primitive for this. From the primitive, you can get a generating function and a phase function. It's a bit of work to do all this, but the point is that eventually you're no longer in the standard setting, but you get this two homogeneous phase function. From this phase function, you can then construct an elliptic Fourier integral operator. So this construction is, people from FIOs would say standard. Once you have, it's not quite the same as in the classical case, because you have a different phase function and different operators, but essentially you're just looking for an elliptic symbol that satisfies these Maslov conditions and construct your Fourier integral operators. You can do this for both C and C inverse. You get your Fourier integral operators with the same conditions. They inverge each other up to smoothing operators, and they satisfy a Egorov type theorem. That's where you have to work for a little bit, but there's some of this in Helfer's book that you can use. So if you have a Shubin type pseudo-differential operator of order M, and you conjugate with these, then you get again a Shubin type operator of order M. And the point is that you not only get one, the principal part of the symbol, but you also get the lower order symbol. So you get this approximation modulo 2 orders lower. So in the standard, recall in the standard case, for Yegorov's argument says if you conjugate a pseudo-differential operator with a Fourier integral operator, then the principal symbol is given by the composition with the canonical transformation. In this case, it's given, okay, the principal symbol is given by that, but the one lower order symbol is also given by that, because from this fact that the symbol expansion drops always by 2 orders. Okay, but then the strategy is the same. We compose with these operators. So we undo this canonical transformation, and we see that if we define J of P by this, then J of P minus P is 2 orders better than we had before. Okay, you see, it's different but in spirit, it's the same as before. You just have to make sure the difficult point was to find this phase function to see what are the correct Fourier integral operators. But once you know this, the machinery works fine. Okay. So now you have to go through the iteration scheme. That's basic, just a lot of work to see that everything works out. Eventually, we get the same result as they had. We find an elliptic pseudo-differential operator, Q, with a parametric Q sharp. So they're both of Shubin type. And we do, again, the conjugation with this. So the first conjugation was with F. The second is with this Q sharp. And then we approximate P up to order minus infinity. So this formula looks precisely the same as in the standard case. Okay, now we have to get from this to the fact that this operator A that Adelheid gives us for free is a Fourier integral operator, and essentially this here. Okay, there we had to find a new argument. Because we couldn't get that of Dijsselmark and Singer to work. What we show is, okay, suppose we have two operators. We're not saying what they are, they just go from S to S. And they're almost inverse to each other in the sense that E tilde and E tilde E give the identity up to smoothing operators. And they commute with these Shubin type operators up to order minus infinity. Then that's what this says. It's a multiple of the identity. The result is the same as before. It's a multiple of the identity for some C0 plus a regularizing operator.
Sorry, Elmar, could we go back to the theorem for just a second? No, the theorem was on that slide.
Which one?
The theorem which was about the proposition you were explaining. The same slide as you were. Yeah, this one, yes.
This one.
The
Okay.
theorem, right? So I'm wondering about the status of P. So is P just arbitrary because it says it exists an elliptic Shubin blah 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 such as that, and then here P is just arbitrary. So should I assume that P simply also exists, right?
Say it again.
I'm confused about the logic concerning status of P. P is something that exists and is arbitrary. So the statement is that there exists this elliptic Shubin Q, and there also exists this P, which is psi infinity, right?
Sorry, may I?
No.
May
This holds for all P.
Ah, okay. Sorry. Okay.
Yeah. We want to the idea is to undo this isomorphism P, right? And we do it in two steps. In the first step, we undo it by conjugating with this F. And we see that was the result before. If we sort of undo it with the F, then we get two orders lower. In the standard case with one order, here we get two orders lower, which we need in the process later. You know, this is the first. This is if we conjugate by this, we get two orders lower. And then we conjugate again with these Qs, and we get infinitely many order lowers. And actually, this is an iterative step where you change these Qs from step to step. So you get 2, 3, 4, 5 orders lower, and eventually, you match the symbol up to order minus infinity.
Yeah. That's fine. Just it would really help to put a quantifier for all P because
Ah, okay. Mm-hmm.
It's very easy to when you write it like this. I was just thinking it didn't make sense to me that just for some p exists. It just didn't make sense to me. But I saw it just written p in psi infinity. Okay, for all p's it makes perfect sense to me. Yeah.
Yeah, that's a good point if you have a talk, right?
Richard wanted to add something.
Elmar said it already.
Okay, good, great. So let's proceed.
Okay, we showed this proposition. That's actually lengthy. We first showed it's a pseudo-differential operator by using sort of a Beals type characterization. That's an idea that's also a little bit implicit in this Mattei-Melrose paper, and then show that once we have this fact implies this, but this is kind of a lengthy argument. Okay, and that was essentially it, right? Because once we have this, we can conclude similarly as before. We have this fact that if we conjugate with Q and F in this way, then we reproduce the operator up to order minus infinity. And we also know that I of P, that should be a capital P, is given by conjugating with this A inverse. And then we want to get into the framework of this proposition. Remember, let me just go back. This proposition says you have two operators that are almost inverse to each other and commute with P up to order, these P's up to order minus infinity for all P, then they're the identity plus a smoothing rest. And
so here you need capital P. Yes, I see it. Okay. Right?
Ah, thanks. Yeah. Yeah, and for these operators, you choose these two parts, right? This is the one we have on the left, because I of P is A inverse PA, so we have Q sharp FC inverse A inverse, and on the right you have A FC Q. And okay, you see right away, if I multiply the two, then they all cancel up to regularizing orders operators. So E tilde is the identity up to smoothing, and E tilde E is also the identity up to smoothing. And moreover, this equation here, if you insert the A's, then this equation says that it commutes up to smoothing operators with all these P's. For this, you have to multiply with the corresponding operator from the right-hand side so that you kill them. But then you get these two equations. And these are precisely the two equations that we had in the proposition. So you have to have this and you have to have this. So the proposition says it's a non-zero multiple of the identity plus some rest. Okay. So that's the same as we have. So E was this operator here. That's the one I just copied. This one here is C times the identity with the rest. Or if I multiply with A from the right, then we see A is C inverse times this operator. And I see again, this is a Fourier integral operator, this invertible. So the whole thing is invertible Fourier integral operator of the Shubin type. Okay, here we use the fact that we constructed the Shubin type pseudo-differential operator of this particular class and a Shubin type elliptic pseudo-differential operator. And this thing on the right-hand side is just a regularizing operator. Yeah, that's good enough for everything. Okay, so we've proven everything. Thanks.
Thank you very much. Wonderful. So we have plenty of time for questions, so please fire at will. Tomek, but show yourself, please. And unmute.
Hi.
Okay. So I have the following question. The pseudo-differential operators and the Shubin pseudo-differential operators are special cases of operators defined in terms of some homogeneity condition. Namely, in pseudo-differential operators, homogeneity for symbols is governed by assuming that x is of weight 0 and xi is of weight 1. In Shubin's version, weights are 1, 1. But you could think about other versions when you have homogeneities of x and xi different from 0, 1 or 1, 1. Then instead of removing the 0 section or the 0 point in R2n, you have to remove some k-dimensional subspace of fixed points of the action of positive real numbers, multiplicative group of scaling. And you have, for instance, also these different weights in the contact case when you have this in the paper of Baum and Van Erp. It's another story with different weights. So your arguments are quite general. So I wonder when there was a lemma which had two incarnations, one for pseudo-differential operators and another one for Shubin. Yeah. So I wonder how far this lemma could be generalized to different weights.
Yeah, but this is already. Let's make this takes forever to move the slides. Here it was. You know, see, this is very general. This wouldn't be the obstacle for us. The most difficult part was to construct this Fourier integral operator. Eventually, this then turned out to be a like one of those that Helfer had studied. But before, when you asked people, should it be this way? And they said, yeah, it should be this way, but they wouldn't know why. As always, you expected. This Idle-Height lemma works, that's fine. And then you have to show that that you get a canonical transformation. You have to see, you'd probably get a special kind of canonical transformation, right? That should reflect your homogeneity properties.
Yes.
And okay, I don't say I know the answer, but yeah, for this you'd have to construct corresponding class of Fourier integral operators. Yeah, might be interesting. Do you have applications might be to context manifolds. That's true. Yeah, I don't know the answer, but it's technically a problem. That's certainly.
In a sense, odd dimensional sphere also is a contact manifold.
Say it again.
The odd dimensional sphere is also a contact manifold.
Okay.
Yeah. You are dividing by the action of multiplicative group of positive numbers, something which is a symplectic space, and then you always obtain a contact manifold. Yeah.
But a very nice.
So the sphere bundles, odd dimensional sphere, they are all cases of contact manifold. So my impression that there must be something more general behind this.
Yeah, I didn't think of it, yeah.
Elmar, just a completely stupid question. Right here, do you mean inclusion? A
Where?
is some kind of algebra, right?
Subalgebra.
Yeah. So is it your notation for subalgebra or?
Yeah.
Okay. Okay, anybody else? And maybe co-authors, collaborators, Richard, Robert, Anton.
Just following up on Tomas's question.
Okay, go ahead.
So another class of things you could try would be these Hermander SCHROHE class of pseudo-differential operators and the Fourier integral operators that go with those.
Yeah, but they have to be classical, right?
So those were ones that had this another kind of funny homogeneity where there's an extra weight in the formula for how the derivatives behave. I forget exactly what the definition is. These are things that are sort of useful for looking at hypoelliptic operaters where the degree of homogeneity is kind of different in one direction than it is in another.
That would give us a similar problem. Okay, you have to see what the canonical transformations are, yeah.
Right, but again, you know, your method might actually work for these things also.
Yeah, I mean, Eilheit certainly is very general, right? You think you could apply to almost everything in this spirit, right? But the difficulty is the construction of the Fourier integral operators. But okay, yeah, the theory is flexible, yeah.
Okay, Richard.
No, so as there's this calculus of what Paul would like. So you would think of kind of Heisenberg-type pseudo-differential operators, or more generally symbols which are with values in some polyhomogeneous Lie algebras. Okay, instead of Rn or so you would have polyhomogeneous things. And as Lemma was saying, the one thing that does not exist, at least at the moment, is construction of the corresponding Fourier integral operators. So pseudo-differential operators exist. There's no doubt about that one. And yes, the automorph, and you would expect, in some sense, you would expect automorphisms of these to give you a definition of corresponding Fourier integral operators. Because with ideal height and lemma, it's just a kind of triviality. So an automorphism of, let's translate it a bit. So an automorphism of matrices is inner, and ideal height's lemma is kind of elaboration on that one. So this holds always.
The proof actually not very difficult. It all goes down to analyzing rank 1 operators.
Yeah, precisely. So ideal height lemma is just it's automatic.
Yeah, but it's extremely okay. Yeah. You could argue both ways, right? It's easy to prove, but it's a very strong result, in my opinion, right?
Well, the result is because it has to conjugating by this thing has to map certain class of operators to certain class of operators. Right. So that's the structure results about particular A that you construct from ideal lemma. And I would almost try to turn it around. So Jonathan's question. So say you think, of
these are your
hypoelliptic algebra of hypoelliptic operators and one of a calculus, and then automorphisms of that one. They will be given by some kind of conduct transformation in any case, and this would correspond to Fourier integral operators in the corresponding calculus. So of course, the analysis is the one thing that is difficult to kind of write down explicitly what do these operators look like.
So it's a
say take Heisenberg calculus, right? Take the automorphism of algebra of Heisenberg operators, and translate that one into kind of Fourier integral operator in this context.
There was one more thing by Alessandro, I think.
Alessandro will have his go, but Paul, because it's related to you, maybe Paul goes first, Alessandro next, okay?
Sorry.
Oh, wait, I can ask a question now?
Yes, please.
Oh, all right.
Well, Paul.
Okay, I would like, so you have two manifolds, X and Y. I would like to assume that they are both closed, that is compact without boundary. Which I think in some sense you have been assuming that. Correct me if I'm wrong.
No. This Dijsselmaat-Singer result goes for any smooth manifolds, but actually Matthei and Melrose assume that.
Yes. Okay. All right. So let's say that X and Y are both closed, meaning that they are compact without boundary.
Yes.
How different can they be? I mean, do you have examples where these two are very different? Yeah,
I mean,
surely they have the same dimension. They must have the same dimension. I mean,
yeah, they're diffeomorphic.
They are diffeomorphic. Okay, that answers my question. Yeah, they are diffeomorphic.
Yeah.
They are diffeomorphic.
Yeah, we even construct this canonical transformation, right? It's
but it's not X and Y. It's the cotangent bundle.
Sorry.
No, I mean,
no, they are not
by themselves. Wait, I have a conjecture about X and Y. Yeah, you prove that the cotangent bundles are diffeomorphic.
I agree.
Cosphere
bundle, yeah. Okay, I have a conjecture about X and Y. I think a typical example for X and Y, I mean, that would be interesting, where they are not diffeomorphic, would be these Milnor 7 spheres. So the Milnor 7 spheres are not diffeomorphic, but they are homeomorphic. I conjecture that in the case when X and Y are closed manifolds, given this hypothesis, the two manifolds will be homeomorphic. Not necessarily diffeomorphic. Do you have an example where X and Y are not diffeomorphic? I'm suggesting that such an example will be the Milnor 7 spheres.
That's the second one. Yeah, it's definitely worth having a look at that. Thanks.
Thank you, Elmar. Thank you for your talk. Thank you for this very interesting talk. I mean, it seems to me that the upshot of all this is that giving this hypothesis of order preserving isomorphism, that the two manifolds will be very, very much alike. I mean, the two manifolds will resemble each other to a very great extent, it seems to me.
Yeah.
So I guess that's my question. Must the two manifolds be diffeomorphic? This, I think that's a question.
Yeah, it's not. Yeah, okay. I first thought this clear.
But I would like to restrict to the case when the two manifolds are both closed, are both compact without boundary.
Okay, I'll have to think of it. I wouldn't know it offhand.
Well, I think, as I am trying to say here, I think an interesting example would be these Milnor 7 spheres. I think that would be an interesting example. I'm guessing, of course, I'm making a guess that with the Milnor 7 spheres, that they will be as in this theorem. That, but they. Well, that's what I'm guessing. Thank you very much for this interesting talk.
Thanks.
Okay, Paul, thank you for your question. So now, Alessandro, prego.
Grazie. But it was actually an error of mine. I like clicked the thing there for the hand, and then I realized, and then it took me a while to realize how to bring it down. So no worries.
Okay, so Anton.
Hi, Anton.
Hello, Elmar.
Hello.
Thank you very much for your talk. I have one question. For these C's, these canonical transformations on this sphere, of course, in your theorem, Fourier integral operators are invertible.
Yeah.
But for general,
they only need to be elliptic. But you can make them. It's not a big deal to make them invertible because, okay, it would be surprising if they have non-zero index. But suppose they have, then you can always compose them with a pseudo-differential operator of the opposite index to make them of index 0, and then you change it by a regularizing operator to make it invertible. So yes, you can assume they're invertible.
But so you can prove the index is 0, or you do not expect the index to be 0?
No, there's this Weinstein conjecture.
Yes, but in this case, it's a sphere.
Yeah, okay, it's different. It's different. Okay, no, I'm saying if the index is non-zero, then I just multiply by a pseudo-differential operator of the opposite index, and that does exist. That because you have, on Rn, you have the this Fedosov index formula, and there you can produce any index. And so you multiply by something of the opposite index. You have index 0, and then you can. It's sufficient to add a regularizing operator to make it invertible. No, because you just have to fill up kernel and co-kernel by smooth functions.
So your canonical transformations are far more than linear transformations, which give these metaplectic operators. You have much more. You have much more.
You can have, for example, metaplectic operators would correspond to quadratic phase functions. So purely quadratic phase function. Here you can have anything that's too homogeneous.
Thank you.
Okay, Tomek, you raise your hand.
Okay, so my question is about this condition for vanishing of H1.
Yeah.
So this is the condition for the existence of the global. How is this function is called? Generating function.
No. This has nothing to do with the generating function. This is, if you see my, do I have?
What is this about?
Your screen is still visible.
Which one? Just the, okay. Just the slides.
Yeah.
Okay.
H1 of S.
Yeah. Sorry. Yeah. What they do is the following. It's in this step. Let's go a little bit further. In this step where you refine this construction, this is here. You have adjusted the principal symbol, and you want to go to higher order terms. So for this, you want to conjugate this with a pseudo differential operator to get the next level. And that they do in local charts. They show that in local charts, you find an invertible symbol. And then they want to patch this to an operator. And so they have to assume that H1 is 0. Okay, because they need to take the primitive of a form. That's where it comes in. This argument we're using, and that actually, okay, this paper by Matteo and Merus in some instances a bit cryptic, but I think they had the same idea, is we show right away that the operator that's still left after you do this first step is a pseudo-differential operator. Just we are very vague about this operator. You know this Beal's characterization. If you have an operator on L2 and all the commutators with xj and dxj are bounded, then it is a pseudo-differential operator in this class psi 0, 0. And you can adapt this to also go to this psi 0, 1 class of pseudo-differential operators, so the standard class. So we see that this A is some pseudo-differential operator, once you have restricted to the same manifold. And then, of course, we don't need this homological argument any longer, because this Dijkstraat-Singer construction locally also gives you a pseudo-differential operator, and hence they have to coincide. And because if you construct something locally, it's the same, and you have something global that has to have the same principal symbol. That must be it. So you can circumvent this this argument by using the Beal's characterization argument.
Okay, so this is the condition for unique gluing of local corrections.
Yeah.
Okay, so patching. Okay.
In the case of a non-compact manifold, in this calculus that Dijkstraat and Singer are using, there it's problematic because there you don't have such a characterization, right? That works for compact manifolds, or for, say, it would also work for uniformly estimated operators on Rn, but not in general. For Dijkstraat and Singer, it's necessary. If you're in a compact manifold, or in our case on Rn with Shubin operators, it's dispensable. Okay, anyway, it would be fulfilled if you have, in our case, it's anyway fulfilled because we have dimension 2 or larger. So that's always simply connected and there's no problem. But for manifolds, there could be.
But I also worry about this globally defined generating function, because if you have this primitive of the symplectic
in our case,
form,
it's local. This is local.
Yeah, but in your result, you do not assume that this graph. Oh yes. So I now understand. So I was right at the beginning, because if you have this Lagrangian graph of your map, then this graph is diffeomorphic. Is even is diffeomorphic with the domain. So if H1 of this is 0, so this means that the restriction of this primitive of the symplectic form to this is exact, producing the global generating function.
No.
So this works also?
No reason for that. Why? That you have contact transform. You have a contact transformation, right?
No, not
okay,
contact. I'm talking. I'm restricting this primitive of the symplectic form to the Lagrangian submanifold. So the differential of this is 0.
Yeah. The
if H1 is 0, so this means that it's exact. So the globally defined genetic function can be found.
No. So you get a function on Lagrangian.
Yes.
Not on the on the whole.
Yes, I see.
Space, right?
You see?
No. It's only local.
If you have a primitive, you get two functions here. You get two functions, say f and g here, and you have to see that there again. given
but
by...
wait a moment, but this Lagrangian is the same as cosphere bundle of y. And this produces this generating function.
No, if anything, it's cotangent bundle of well,
No,
this
I'm talking
is
Lagrangian with respect to this product.
No, Lagrangian is just a Lagrangian T0 star X cross T0 star Y,
yes.
period.
So the graph of this...
it's Lagrangian. Locally, yes. It's a graph of something. Locally, it's a graph of something. Just locally, not globally.
The variables you have to
No, it's a graph of a canonical transformation.
No. Well,
it's a graph of a canonical transformation.
That's true, right?
Yes, sure, but not no. But that's because of one homogeneity. But you should not think of it as a what's the word? It's a graph, but you have to choose different coordinates, different places.
Just
okay,
just imagine that, you know, a simple example is if you have all fibers in X direction or all fibers in Xi direction, and then you have to use different coordinate systems, right? That they could move from one to the other.
There is canonical transformation, right? Just flipping flipping X variables and cotangent variables. It's a canonical transformation. And locally, you can find the phase function.
But globally, it's not.
Globally, there's no reason for that.
But if H1 of the cosphere bundle is 0, then restricting this primitive of the symplectic form to this is there is a differential of a function, and this function is true.
That's completely true, but that doesn't give you yet.
So S is something different.
Yeah.
S is not a genetic function in my sense.
S is defined on the whole cotangent bundle, not just on the Lagrangian. In the function of the cotangent bundle, not just on the Lagrangian.
But this Lagrangian is diffeomorphic to the cosphere bundle, or not cosphere, to T star Y.
T star 0 Y.
T star 0 Y. So this is a function on this.
Yeah. Okay. But
so I'm confused. Is my S, my generating function, which is primitive of the restriction of the primitive of the symplectic form to this, so the graph of this canonical transformation different from your S?
If you take just a primitive of the one form, right? Then you just get two different functions here.
No. The graph is isomorphic with T star 0 Y.
Yeah, that's true.
So function on a graph is a function on T star 0 Y. So it's a function of Y and Xi. So so H1 vanishing is
but Xi is a covariable of the X.
Yeah.
Xi is a covariable of the X. So you have Y on one side and Xi on the other side.
If it's a graph, it's a diffeomorphic to the domain.
That's
yes.
So it's a function of Y and Xi. And this is called the generating function in symplectic geometry.
Of Y and
is this phase function different from that?
I'm saying, but the coordinates on the domain would be Y and eta. You said Y and Xi.
It's the wrong coordinates.
Oh, I see.
It's the wrong coordinates.
Yeah. So this phase function is not this function, generating function. Okay.
So phase is not the generating function. But
I wanted to understand the difference. Yes. Thank you very much.
In classical mechanics, you would write a small p and big Q, or vice versa.
Yeah.
So it's some coordinates on one side and some coordinates on the other.
Yeah. So there is some shift in this cotangent variable. You have this psi instead of eta. Okay, I understand now.
Mm-hmm.
Now I understand the difference. Thank you very much.
Okay, so this has been happily resolved. I don't see any raised hands, and we have already spent some time, so it's your last boarding call for a question. Okay, no questions, so let us thank ELMAR again. So thank you so much. Let me stop recording. Yeah, this was great to have you here. Let me stop recording. Please don't go away. I stop recording.